From one of our simulations of a little piece of a lipid bilayer, a simplified version of the cell membrane. At the very top and the bottom of the image, you'll see the water molecules that would be inside and outside the cell of the sphere cell membrane, and the red, blue, and gold spheres are the head groups of the phospholipids that make up the bilayer. And the gray kind of shadowy lines in the middle of the screen are the lipid tails that form the interior of the membrane. What each one of these little particles in the model is an atom, and we assign to each one of these atoms a charge and a position at the beginning of the simulation. This is actually three-dimensional. It's projected onto the screen. And then we use simply Newton's law of motion, Newton's laws of motion, and the Coulomb's law of electrostatics to calculate how these atoms interact with each other over time and when the electric field is imposed. And we'll start the simulation now, but you can see before the field is applied, the system is in its lowest energy configuration. And the water molecules in particular are randomly oriented. Water molecules are dipoles though, so when we apply the field, you'll begin to see things move as they do, and then we're looking at just a few nanoseconds here. When we apply the field, you'll see under the influence of the field, the water molecules become more stable in a column, in a stack of water, than they do in a sheet as they are without the field. And because of this, they tend to line up, as you can see here, and we'll just stop it for a second. And you can see these water molecules are actually, the red with the oxygen is actually oriented upward in the field. The field is going downward with the positive at the top and the negative at the bottom. And the water molecules prefer to stack up like this now when the field is there. So eventually, as we continue a few more nanoseconds, we see a column of water form, and then the phospholipid head groups, which are charged, follow the water, and the pore is formed. And now we have a column of water from one side of the membrane to the other, and material can pass through this pore, such as ions and small molecules, bypassing the normal barrier function of the membrane. What we learn from these simulations is that if you develop a potential of approximately 400 millivolts or more across the bilayer, these pores will form very quickly within a few nanoseconds. And because when we use nanosecond pulsed electric fields, we see these large transmembrane potentials everywhere in the cell. It's not only the plasma membrane that's permeabilized, but also every membrane in the cell. The mitochondrial membranes, the endoplasmic reticulum, vesicles, everything.